for ATS 114 lab. This is Dr. John Schrage, and I'm just giving you the little tour to make sure that we're all clear about the vocabulary words and how to do this lab. This is not the video I'll be giving the students, obviously. This is a different one, but I wanted to kind of walk through. And so since I now have a digital copy of the text, I just sort of cut and paste some pages out of there into a PowerPoint as just sort of a scrapbooking method, and I'm going to show you how to do. Now, in this week's lab, you're going to be doing parts of Labs 3 and parts of Lab 4. They're both labs about radiation and how they affect temperature at the surface of the Earth, and they both contain some things that don't sync up very well with our textbook. Either the things we're not there yet on, or things that are not in the textbook that we use at this school. So let's just sort of take it, and I'll show you what's all there. Okay, so let's talk about some of the parts that are in Lab 3. There's going to be some questions that involve computing the amount of radiation that's being emitted, and right there on the bottom of the page, first page of this lab is...
messages received from Paul Schrage.
Just a second here. My phone is going nuts today. There we go, I've got that turned off. Okay, so you're going to be using Stefan Boltzmann's law, which is this E equals sigma T to the fourth thing, and sigma is just a constant, and T is just the temperature in Kelvin. Now, there's actually a typo here, at least in the digital copy of the book. They aren't canceling the units right here, but they ended up with the right answer because, you know, they knew what the right answer was going to be. Just tell them that the units of this energy that's being emitted are going to be watts per square meter, and that's more than enough. They don't need to worry about how they're going to cancel all these units and so on. So, like, for example, the first problem of this lab, the sun has an average temperature of 6,000 Kelvin. How much radiation is emitted from the surface? You just plug in the numbers from the Stefan Boltzmann law on the previous page, and you'll get a giant number that is the amount of radiation that's being emitted on every square meter of the sun's surface. And then you do the same sort of thing for the Earth's surface using a temperature of 300 Kelvin, which is puzzling to me because in the example, the calculations and stuff they did in the beginning of the lecture, they actually used a different number than 300, but whatever. If you use 300, you should get the right answers there. Similarly, if you went over there, there's this weird set of questions about number 2. It wanted you to take the sun's temperature and divide them by each other. I mean, that's just, again, if you use 300 for the temperature of the Earth, you'll get the right answer. Then they tell them to take that answer and raise it to the 4th power, and they wanted to show you that it is equal to the ratio between the Earth and the sun's amount of emitted radiation. I mean, that's interesting. You know, basically you can use the temperature then to the 4th power as an estimate, but I mean, it's kind of just algebra. I don't really know what the teaching value of this is. Okay, so then when you take that there, let's see here. That was question 2. If we move on to question 3 here, question 3 says calculate the wavelength of maximum emission for the Earth and the Sun. Again, if they've read the text right above there, that's what Wien's law tells them. This is the 2 different radiation laws that they actually learn in the class. Wien's law tells you that the wavelength of maximum emission, lambda max, is just, and then there's this very simple relationship. So if you just plug in the temperature of the Sun and the temperature of the Earth using that constant C, they'll get the wavelength of the radiation in microns, and then the problem 4 actually has them go down to that table below there. They'll have come up with a value of the wavelength of radiation being emitted, and they'll find out, you know, they'll go through there and say, oh, it's in this range, oh, it's visible light, or oh, it's microwave radiation, or whichever one it is. Then there comes a kind of cool part of the lab here that is about the fluxes of radiation at the surface of the Earth. This is about the shortwave radiation coming from the sun, hitting the surface of the Earth, some of it getting absorbed, some of it getting reflected, and then the same sort of thing for the long-wave radiation being emitted by the Earth's surface and long-wave radiation being emitted by the clouds and greenhouse gases in the atmosphere. The sun does not give off, well, the sun gives off lots of long-wave radiation, but it's also 93 million miles away. From the point of view of the Earth's orbit, you can effectively say that all the shortwave radiation comes from the sun and all of the long-wave radiation comes from the Earth and the atmosphere and clouds and things like that. That's why we use the word solar radiation to describe shortwave radiation, and we use the word terrestrial radiation to describe long-wave radiation. And see these symbols, SW up, SW down, long wave, LW up and LW down. Those are like pretty standard notations, at least in education and atmospheric sciences. Your book uses, the lab manual uses slightly awkward words here. I mean, they're actually technically right. Incoming shortwave radiation being SW down. That would be radiation coming from the sun and reaching the surface of the Earth. outgoing shortwave radiation would be SW up, the radiation that's escaping from the Earth and going up into space, and then long wave down is the long wave radiation coming from the sky down towards the surface of the Earth, and outgoing long wave radiation is the long wave up. And again, most textbooks use, like, they don't usually say this incoming and outgoing thing. They usually just say long wave up, short wave down, and long wave down. Oh, I didn't really actually have this verbiage here in case you haven't seen it before. Shortwave down is the shortwave radiation that has made it through the Earth's atmosphere all the way down to the surface of the Earth. Whatever, obviously some of it was lost as it was like reflected off clouds or absorbed by little aerosols in the atmosphere and so on. Shortwave down is what actually makes it to the ground. If you had an instrument here at the ground or a solar panel at the ground, how much radiation made it this far? Shortwave up is the radiation that got reflected off the surface of the Earth. It's from the sun, but it got reflected off the surface of the Earth. Net shortwave radiation would be the difference between those two, and that would be the amount of radiation that's actually being absorbed, shortwave radiation that's actually being absorbed by the surface. Long wave radiation is radiation that is being emitted by the surface of the Earth. So long wave up is radiation that if you had an instrument at the ground, point it down and measure the long wave radiation coming up, that's long wave up. That's radiation that the surface of the Earth is giving off. The amount is just determined by Stefan Boltzmann's law. Long wave down is the amount of radiation that's being emitted by clouds and greenhouse gases in the Earth's atmosphere. This is long wave radiation coming from the sky down to the surface of the Earth. Again, the amount of radiation is determined by the Stefan Boltzmann law and by the amount of clouds and greenhouse gases in the atmosphere. I mean, if the atmosphere has no clouds, there's going to be less long wave radiation coming down from the sky to the ground. Same with greenhouse gases, water vapor being the one that varies the most. There isn't very much fluctuation in the amount of carbon dioxide in the atmosphere. There's this neat example here of, this is actually something real scientists do in atmospheric sciences. They put out these radiometers and they measure the fluxes of shortwave and long wave radiation up and down at a location. This is pretty cool, and this is a 24-hour period where you can see how, like, the shortwave down was 0 until sunrise, and then it increased until noon, and then it decreased until sunset, and so on. You can see how the shortwave up was 0 until sunrise, and then some fraction of the amount of radiation that was hitting the ground got reflected back up to the sky, and you can see the same curves for long wave down and long wave up. But here's the deal, this is a pretty cool figure, and you might want to use it when you're showing it to students as an example, but this one is not actually used in any of the questions. Instead, they use these much tinier little ones that have two little figures here. There's a total of 6 days of data here. The top panel has 3 days of observations from a piece of equipment in someplace in Africa. It's in Mon, Botswana. Anyway, I'm an African meteorologist by training, and I've never heard of Mon. This is so there's 3 days of data on each of these graphs. The top panel is for 3 days in February, and the bottom panel was 3 days in August when they had this piece of equipment deployed in Botswana. And question 5 says, first off, looking at these graphs, why is incoming shortwave radiation higher in early February than it was in early August at this location? Again, what you're doing here, it might not be clear what's going on. If I just sort of drew a little green line on each of those two plots that showed, like, the peak of the shortwave down curves, like that's roughly how much radiation they're getting, at noon or something like that. See how the peak in the top set of panels for February is way high, like 1,100 watts per square meter, and the ones down there in August, the peak's more like 800 watts per square meter. The question's asking is why that would be. In the verbiage in the text that they tend to not want to read, this station in Botswana is in the southern hemisphere. It's actually very close to the Tropic of Capricorn. So in February, it's just got higher sun angles than it does in August. I'm not, it's not exactly rocket science once you know where the location of this is and how to read this diagram. Zooming in a little bit here on question 6. The question 6 says, at solar noon, the radiation values at the top of the atmosphere at Mon are 1366 watts per square meter and 10 in February and 1074 watts per square meter in August. Why are the values at surface solar receipt shown in those figures so much lower? Okay, what's going on here? If you actually, again, add some little lines here, what they're trying to say is, take the February diagram there. We know that we've got a peak of about, what does it work out to, about 1,100 watts per square meter is the most amount of radiation that's ever making it to the ground over this station in Botswana. And they're saying, but actually if you're above, at the top of the atmosphere, I have it circled there, at the top of the atmosphere above Mon, the actual flux of radiation from the sun is 1,366 watts per square meter. The reason why there's a difference here is because so much of the radiation from the sun is actually being either absorbed or by gases and clouds, or reflected by gases and stuff. It doesn't make it all the way down to the surface of the Earth. That's all there is. It's just absorption and reflection of some solar radiation by gases and aerosols. I mean, we tend to think of the atmosphere as being pretty transparent to solar radiation, but we do actually lose a chunk of it. It's mostly stuff, though, that like our eyes don't see, like ultraviolet radiation and stuff that's actually getting lost here. Question 7 is pretty tricky. It says, based on the incoming shortwave radiation curve, which was cloudier, February or August? What I want you to notice here, let me see if I can get my pen. I'm going to use my pointer felt tip pen. See, in February, these curves are really smooth for the shortwave radiation. Okay. That's just the slowly changing amount of sunlight over the course of a day. The sun came up, the amount of sunlight increased until noon, and then decreased until sunset. In contrast, if you go and look at February, see how there's these like notches and divots and so on in this solar radiation curve here, shortwave down? Each of those is when a cloud was passing by, briefly reducing the flux of shortwave radiation down to the surface. So the right answer is that February was cloudier at this location. Number 8 was too easy. I didn't even bother making a little key type thing there. For number 9, thinking about the radiation laws, why does outgoing long-wave radiation from the Earth's surface exceed the long-wave radiation received by the... why does outgoing radiation from the Earth's surface, here, that may be useful to you guys. Make sure that you understand the question here. From the Earth's surface exceed the radiation received from the atmosphere. So what they're saying here is, see how in all of these curves, long wave up, which is this curve right here, is always greater than long wave down. Okay, well the answer as to why long wave up is always more than long wave down in these graphs is to think about what's doing the emitting. In long wave up is being emitted by the surface of the Earth. Long wave down is being emitted by cold things like clouds and gases up high in the atmosphere. So, well, especially at a fairly tropical location like this place in Botswana, the ground is certainly going to be warmer than the clouds and gases are. So by Stefan Boltzmann's law, you would expect the ground to be emitting more radiation than the atmosphere is and the gases are. Question 10 says, look closely at the curve showing long-wave radiation emission from the surface of the Earth on 6 dates. Explain what counts for the general pattern you see each day, and what causes the difference in the magnitude of the peak of the long-wave radiation between February and August. It's easy to get bogged down in this question and not see that the key word here is the long-wave radiation being emitted by the Earth's surface. They're just talking about this long-wave radiation curve. They want to know why is it got this this diurnal cycle. If you don't know that word, diurnal means like a 24-hour cycle. Okay, it's a word actually that meteorologists misuse. That isn't actually, if you look up in the dictionary, what diurnal means, but diurnal as in on a 24-hour cycle. So, well, I mean, then once you know that that's what that means and you catch that phrase in there that we're talking about the long-wave radiation being emitted by the Earth's surface, well, then it's pretty simple. I mean, the ground is hotter in the afternoon than it is in the night, and so the ground emits more long-wave radiation in the afternoon than it does at night. That's just why you're seeing that little cycle there. Number 11 is just filling in a couple 3 values in a table. It's just an arithmetic thing. As long as they follow this little equation right here, they should be in good shape. Questions 12 and 13 are a little bit tricky. 12 is saying to look at this graph here that has over a 24-hour period the net radiation. This net radiation is what they were just figuring out in the table before. It is the sum of the long wave up, the long wave down, the short wave up, the short wave down, to figure out overall is there heating or is there cooling going on by radiation processes. So if they notice that there's a 0 line on this y-axis, it'll be helpful. I know from experience that with similar labs, the students just sort of assume the 0 line is at the bottom. And so notice that the y-axis has a 0 line right there. It's a little confusing. Students might not have familiarity with how to work with a 2-axis diagram and stuff like that, with 2 y-axes like this. But anyway, you'll get that sorted out. So see, that net radiation curve is just the balance from all that short wave up, short wave down, long wave up, long wave down, etc. And anytime that the net radiation is positive, it means that the surface is gaining more heat by radiation than it is losing by radiation. So you expect the temperature to go up. Anytime the net radiation is negative, the surface is losing more heat by radiation than it is gaining by radiation, so you would expect the temperature to go down. So for example, we expect the temperature to increase when net radiation is positive, even if it's a small positive number. I mean, if you actually look at this graph here, like late afternoon, net radiation is actually not that high. It's a positive number though. It isn't as high as it was like at noon. Well, you might be confused as to why the temperature keeps going up. Well, even though the net radiation isn't all that big, it's still positive. You're still gaining more heat than you're losing, so the temperature tends to go up. In the same way, at night, all night long, this net radiation was negative. So all night long, we are losing heat. And so the temperature just gets lower and lower and lower. And it isn't really until sunrise, or strictly speaking, actually shortly after sunrise, that the net radiation becomes positive again and temperatures start to rise. Skip the rest of Lab 3. Some parts of it are things we haven't covered yet. Some parts of it require an online activity that never works quite right. So go ahead and just skip the rest of it and go look at the review questions. Now, on the first review question there, as long as they understood that the word seasonal here means like over the course of a year, and that the word diurnal means over the course of a day, that question should not be terribly difficult. The question 2 for the review questions is asking a question about like, if you knew that tomorrow was going to be cloudy, how would that affect your forecasts of the high temperature and the low temperature tomorrow? Like maybe in comparison to a sunny day the day before or something like that. And the high temperature, that's not really all that hard. I mean, you would think that if it's going to be a little cloudier than it is today, it'll be a little cooler tomorrow. That's easy. I'm not really sure how they're supposed to know the answer to the low temperature part of the question. I mean, the answer is that it would be a little warmer at night if it's cloudy, since the clouds are going to be emitting long-wave radiation down towards the surface of the Earth. I actually happen to have mentioned that to my students in intro, but I don't know that it's like in the book or anything, and I'm not sure whether I would expect the other sections to have done that. So that part of the question might require some feedback from you guys. Now, real quick, the parts on numbers lab 4, we're only doing a couple questions here. There's actually several questions that come and use this diagram from page 38. So let me explain the format of this diagram real quick. Both graphs are going to be showing some quantity over the course of a year. See how the y-axis is like time over the course of a year, January, February, March, all the way up to December. The left graph is just showing you shortwave down, where that is the 4 different curves or 5 different curves there are just showing at different latitudes how much shortwave radiation down are we receiving in January, February, March, April. So we have like 4 different latitudes or 5 different latitudes there where we're seeing the amount of shortwave radiation down we're receiving each time of the year. And the same is true on the right graph, except instead of it being shortwave down, it's just the temperature. Okay, so once you understand the format of that graph, it's not actually so difficult to like start figuring out how to answer these questions. But question 1's kind of weird. It says at 5 degrees latitude, there's actually 2 peaks in the incident solar radiation. In other words, the shortwave down during the year. Why does this location differ from other latitudes that only have 1 peak? Let me show you what they're talking about here. See, I just highlighted the curve for 65 north. See how it has 1 peak over the course of the year? Not surprisingly, it's in July when it gets, or June and July when it gets the most radiation. Here, I'll do the same thing. I'm highlighting 45 north. See how there's one time of year where it's getting the most radiation, and it's in June or July? Heck, I could even highlight 45 degrees south. Now, it's the opposite here. The time of year in which they're getting the most radiation is actually December and January, but there's only one time of year that it's getting the most radiation. And then you look at 5 north. Well, what's going on here? Why is 5 north getting 2 peaks to the maximum amount of radiation? Well, it's because 5 north is in the tropics. It's actually between the Tropic of Capricorn and the Tropic of Cancer. And so the sun actually passes directly overhead twice over the course of the year. Once on its way to the Tropic of Capricorn, and then once on its way back across that location on its way to the Tropic of Cancer. So there's actually 2 times. I'm not sure exactly what that has to do with global energy budget, but it's certainly an interesting point for them to have remembered how that all works. Question 2, again, it's not the most clearly worded question. The Earth in its elliptical orbit is closest to the Sun in January and farthest from the Sun in July. What evidence is there in Figure 4.1 that this is true? Well, I want you to take a look here at the peaks. Hold on for just a second. I'm going to bring up something else in a different window. Hold on. look at the peaks for 45 degrees north and 45 degrees south. See how the peak in the shortwave radiation down is greater at 45 degrees north than it is at 45 degrees south? I mean, at 45 degrees south, they actually get more radiation at their peak time of year, which happens to be January, than 45 degrees north gets at its peak time of year. And that's simply because the Earth is closer to the sun in January, when 45 south is hitting its peak, than it is in July when 45 south is. Sorry, I had to cut and paste that and I didn't make a mistake. 45 north is hitting its peak. Hold on just a second. Okay, sorry. A student was texting me and I wanted to at least say okay. All right, anyway. Describe the general relationship between latitude of absorbed radiation and seasonal temperature range. This question, again, is not very clear. You're going to need to help them a little bit with this, and I'll try helping in the video too. What I want you to notice is to look at those seasonal temperature range and see how it varies with respect to latitude. If I just sort of pull up my pen here again. Seasonal temperature range. See how some latitudes there's a huge range between the most and the least? And then there's other latitudes where there's very little range between the most and the least. All I want you to do is notice that there in the tropics is where there is the least seasonal cycle, and at the mid-latitudes and high latitudes are where there's more seasonal cycle. And then when you actually go and you look at those seasonal cycle of shortwave down, you see the same pattern. That's really all they're looking for, and the question is just not that clearly worded about that. Now the last question I want them to do is number 4. And number 4 involves this nifty graph that is about a graph that shows you some important things about the distribution of albedo, or the reflectivity of the Earth's surface for shortwave radiation from the sun, and how it is distributed and how it changes over the course of the year. So this diagram has an x-axis that just shows you at different latitudes, and then, okay, so yeah, at a range of different latitudes on the x-axis there, we are seeing the average albedo or reflectivity for that latitude. So like, you know, at 45 degrees north, I'm not sure if I'm going to be able to see my pen here. At like 45 degrees north in January, the average albedo is 40%. And then like at 75 degrees north, the average albedo is like 90%. Okay, why is the albedo higher at like 75 degrees north? Because there's more snow cover. Snow is very reflective. And so wherever there's more snow and ice, the albedo of the surface will be higher because we're reflecting more of the radiation from the sun that hits it. So notice that at high northern latitudes, high and mid latitudes, there's a huge cycle to the albedo. Albedo was high in January and it's low in July just due to the snow cover that's there in the winter. Okay. Now there's some evidence you can kind of see that at some of these high southern latitudes as well, but there's a big area in the middle where there's basically no difference between the albedo in January and July. Now, at tropical latitudes, that's kind of easy to understand. I mean, there just isn't really any snow cover any time of year in the tropics. But the book makes a bigger deal of one detail here. Notice that the latitudes at which there's basically no difference in the albedo between January and July extend farther poleward in the southern hemisphere than in the northern hemisphere. See, look at like 45, 50 degrees south, way down almost to the coast of Antarctica. There's still almost no annual cycle to the albedo. In contrast, even as far south, even as far equatorward as like 35 degrees north, you start seeing a difference between the seasonal cycle in July and in January. Okay, I don't know why the book makes a big deal about this. It's actually quite interesting. It's more of a physical climatology thing. The answer is because those latitudes in the southern hemisphere are almost completely covered with oceans. If you bring a globe to class or a big map of the world to class, you're going to see there's basically no land at like 35 to 45 to 50 degrees south is south of South Africa. It maybe catches a little bit of southern South America, but by and large you're in the Southern Ocean. All the way around the world, that part of the world, you're in over the ocean. Well, even in the middle of the winter, there's no snowpack on the ocean. Even if it does snow, it just lands on the water and melts. So there's really no change in the albedo over the ocean like that. I don't know why they make such a big deal about it in this lab manual. But that's the end. The rest of Lab 4 is not material that we've covered in our textbook. I think that is actually material that's covered. It's designed to go with a particular textbook that is not the one we use. So that is not merely material we haven't covered. That is material we're not going to be covering. So it wouldn't be helpful. Even the review questions in Lab 4 are not helpful. All right. So they do pieces of Lab 3 and pieces of Lab 4, and it should fill up their time pretty well. Please let me know if you have any questions, and I'm going to finish putting together a decent version of this kind of material that I'll be sharing with, that you guys will watch with the students. Okay, please let me know if you have any questions. This has been Dr. John Schrage.